as Joachim, I want to start off with a nice picture here. What you can see is a so-called globular cluster. It is actually not too far from our solar system. It consists of a few million stars, which are orbiting around a very dense center, which is also very bright here in the middle. And this object is actually quite spherically symmetric. And it is speculated that there's a black hole in the middle, but of course that is very hard to detect. So this might motivate the system we are using in the fact that we are using Einstein's equation to model, for example, such a situation. All right, so a question which one might ask is, are these configurations stable in some sense? So imagine that there is another globular cluster or something like this, which flies past this globular cluster here. And you could ask, does this globular cluster then respond somehow? Does it collapse? Does it disperse in some sense? So this will do for the motivation of our system, I think. So this is what we are modeling. And I hope that this talk won't be too technical because it is, well, a numerical analysis. Yeah, but anyway, I want to show the system, first of all, in its full generality. So basically, we look at a space-time M, on which we have a Lorentzian metric G. And on the corresponding phase space, we have a number density F, which, well, is defined for some time-like variable T, some space-like variables X, and the canonical momentum variables P here. Here already we have put into some assumptions, for example, that we are looking at particles which only have mass equal to 1. So normally we would have a phase space which is 8-dimensional, but this reduces the phase space in 1 dimension because we can, for example, solve for P0. And we remain with a density which is defined on in a time variable and on a 6-dimensional phase space. All right, so we only assume that the particles interact via gravitation, so there should be no collisions because, well, they are quite rare, speaking about galaxies, and there's no electromagnetism or any dissipative forces here at act. And this, together with some basic conservation laws like conservation of particle number and mass or energy, we can write down this Einstein-Vlasov system in general. So we first off start with the law for gravitation, which is basically given by the Einstein equations. I think even though this conference is about general relativity, these actually were never on the slide before, if I recall correctly. So on the left, we have the Einstein tensor G, which tells you how the spacetime is curved. And on the right-hand side, you have the energy momentum tensor T, which tells you where the matter or the energy is located in the spacetime. Okay, so this should be the law for gravitation. And of course, we need a dynamical equation for F, for our number density, which should model our galaxy. And this is the Vlasov equation, which is given by this term here. It probably can be interpreted as some kind of transport equation where we have these canonical momentum variables, and also the metric goes into this via these Christoffel symbols. I don't want to go into more details because we will restrict ourselves to spherical symmetry later on anyways, which makes this much easier to understand. Okay, so anyway, we need a way to couple these two equations, the law for gravitation and the Vlasov equation. And we do that via the energy momentum tensor. So basically we integrate F over the momentum variables with different weights. And with that, the energy momentum tensor again lives on the space-time, and this couples the system. So if we then assume some boundary conditions, for example, like asymptotic flatness, one could study this system in general. But for our purposes, this is much too difficult, actually. So we would have a 6-dimensional phase space and a time-like variable. And this is very hard numerically. Even axisymmetry is quite tough, as we have seen last year in this conference. So we will restrict ourselves to spherical symmetry, as I already have said. So in general relativity, of course, you have you can choose a coordinate system to describe your space-time. And we mainly use Schwarzschild coordinates here. So we only have 2 metric components, mu and lambda, which are unknown. T is some time-like variable, and actually it can be interpreted quite nicely because it is the proper time of an observer which looks at this configuration from spatial infinity. And R is some radial coordinate. And on the right-hand side, this part of the line element basically corresponds to spherical symmetry. Right. So, of course, we have to give some boundary conditions, as I have already talked about before. So first, we describe that we have an asymptotically flat space-time, so that lambda and mu vanish at spatial infinity, which if you put it into these line element, we get Minkowski space at spatial infinity. And at the origin, we demand that lambda vanishes as well. This is needed such that the space-time is sufficiently smooth. So these are the boundary conditions. And a more technical point here is that we also use so-called non-canonical momentum variables. So on the slide earlier, we have used these canonical momentum variables, but analytically and numerically, these don't work as well. And these non-canonical momentum variables, which basically give an orthogonal frame in the phase space, lead to the fact that the energy momentum tensor gets decoupled from the metric components. So this is quite nice because we then have a much nicer ordinary differential equations for the Einstein's equations, which we will see on the next slide. So overall, choosing the space-time and these boundary conditions like this, we get a spherically symmetric space-time, and F lives on the corresponding phase space and is also spherically symmetric in the sense here that if you rotate in X and V at the same time, you leave the distribution function unchanged. So this is the normal notion of spherical symmetry for such a Vlasov system. Okay, so we can now specify how this system actually looks like by putting this ansatz for the metric into this Einstein-Vlasov system on the first slide. And the equation for F looks quite similar. We have a transport-like equation for F, which includes these momentum variables V, the spatial variables X, and the metric components. And then the Einstein equations, which are, of course, very difficult to solve, they reduce to a few equations which are actually quite nice. So this one right here for lambda, for example, can explicitly be solved if the right-hand side is known. So rho is corresponds to the energy momentum tensor. I will show you what it is right here. And this is basically an integral over those non-canonical momentum variables V, and can be interpreted as a mass density. So if we know lambda from this first equation, we can then also solve for mu. And P on the right-hand side is also, can also be interpreted as a physical quantity, which acts like a pressure term. All right. So as you can see, these terms rho and P actually do not have any metric components in them. This was by design because we have used these non-canonical momentum variables. So as it is stated here, it might look like we have gained not that much from spherical symmetry because I still have x and v, which are vectors in R3. So the phase space still looks 6-dimensional, but it turns out that you can reduce the dimensions in which this function f actually lives. So you can describe it with some time t, and the phase space can be described with a radial component, a radial momentum, and an angular momentum, for example. So in fact, the phase space is only 3-dimensional here. So reduced from 6 to 3 dimensions, which makes numerical life much easier. Okay, so another few words about the system together with the boundary conditions. And if we impose that we have the initial distribution, which is compactly supported and in some sense smooth, we know that local in time solutions exist. This was done by Gerhard Rhein some 20 to 30 years back. But it is still an open question if these solutions actually exist globally in time. It should or could be the case because using Schwarzschild metric, this metric basically avoids singularities. So there's a good chance that this might happen, but not very much has happened in that direction for quite some time, sadly. So this is an interesting open problem, but not really relevant for us here. Okay. So as I've already showed you, these Schwarzschild coordinates have quite a nice structure. We can solve for these matrix coefficients explicitly, at least if we know the source terms rho and p. But the main disadvantage, if you might call it that, is that you can't detect so-called trapped surfaces in the Schwarzschild coordinates, as we have set it up here. And so what is a trapped surface? It is basically a surface in space-time where outgoing and ingoing null geodesics always point inwards. So physically speaking, if you look at light rays inside of that surface, they always tend inwards, which might remind you of some notion of a black hole. And in fact, it was shown by Penrose in the 1960s that the development of such a trapped surface always signals that there will be a singularity in space-time at some developed in time, so to speak. So for numerical reasons, we might be interested to detect such trapped surfaces because we then don't know that the space-time will develop a black hole eventually. So this is one reason why we use these so-called maximal areal coordinates as well. So this uses a different gauge on the space-time, which introduces a new factor beta here. So if we set beta to 0, we actually get exactly the Schwarzschild coordinates via taking some logarithms. So this term beta now appears in the metric, and this allows us to actually detect trapped surfaces. But the problem is that the field equations get much more difficult to solve because we have another field equation which we have to solve. And this is also more difficult numerically. We get some kind of elliptic type equation for this lapse function alpha, which is quite nice, but not that useful as one might think in the first moment, sadly enough. Yeah, but I have shown in my master's thesis that also local in time solutions somehow exist in this coordinates. Is a question.
A and beta are time dependent?
Yes, yes. So mu and lambda are time dependent, and A, beta, and alpha are also time dependent. Yes. I have left that out for clarity reasons because then it wouldn't fit in one line. All right. Where have I left off? So exactly. For this, the equations are a bit more difficult. I don't want to bore you with the details because in our talk, in my talk, I only want to focus on the Schwarzschild coordinates, but we have studied the numerics also with these maximal areal coordinates, and we found that stability is very coherent across these coordinate models, which is quite nice because, well, nobody really can guarantee you that stability might not, in some sense, depend on the choice of coordinates which you have used. At least there's no theorem to our knowledge like this. All right. So what is the main question of our work here? We want to investigate stationary solutions to this Einstein-Vlasov system. And we want to find out what is the stability behavior if you perturb such stationary solutions slightly. So first of all, we have to consider how do we construct stationary solutions. This is quite well documented in the literature. And I will recap that here. Then, of course, I will keep this very short, I think. We have to talk about how we simulate the system numerically. And then we will also talk about what is actually known about stability up until now of the system. So numerically and analytically, there are a few results there, which are actually rigorous. And then we will also talk about the new results of our work. So we first of all start off with the first point, how to construct such steady states. And for those Vlasov systems, there's always one nice way to construct stationary solutions, which uses an ansatz that the distribution function f can be written of the form that it only depends on E, and E can be interpreted as the particle energy. So we use an ansatz function phi, such that f only depends on this particle energy. And such a ansatz always, by construction, solves the Vlasov equation because E is an integral of motion corresponding to the characteristic system. So every ansatz of this type solves the Vlasov equation automatically. And of course, this is quite good because the Vlasov equation is nonlinear and we don't have to worry about this anymore. So for technical reasons, we write the ansatz function in this form on the right with a cutoff energy E0. So this cutoff energy is actually needed to obtain compactly supported stationary solutions which have a finite radius. So, this is physically reasonable and also numerically, of course, very valuable. All right, so as we have already solved the Vlasov equation by construction, this basically only leaves the field equations which we have to solve. And it actually can be reduced to one ordinary differential equation for this quantity y here. So this is basically just this metric coefficient mu shifted by some by this cutoff energy E0. And yeah, the ordinary differential equations we get out is this one right here, where on the right-hand side we have appearing functionals which depend on the ansatz function phi, which we have prescribed in the beginning. And these terms which appear here can be interpreted as arise from the fact that you put the ansatz function phi into these source terms rho and p. So this is the interpretation here. And this in itself is some kind of ordinary differential equation. We prescribe now some initial value y0, which is bigger than 0. And we look for solutions of that system. So these solutions exist under some reasonable assumptions for phi, which I will comment on in a few minutes. So if we do solve this equation for an initial value y naught, we get a whole family of steady states for this ansatz function phi, which for historical reasons, you might call it, we do not actually parameterize with that initial value y naught, but with a so-called central redshift set, and which is in more or less in one-to-one correspondence to y naught. Because, well, the physicists who looked at the system before always use this factor right here, because it has a nice interpretation that it describes the redshift of a photon which starts in the center of the galaxy and is then received at the boundary of the galaxy. So in particular, if this central redshift value is very large, we know that there is a more relativistic setting. And if this central redshift value is very small, we know that we don't have a relativistic setting. So it's a measure for that. Okay. So do these static solutions exist? This was done for a large variety of ansatz functions phi by Ramming and Ryan some 10 years ago. And they showed that such solutions have finite mass and that they have compact support and that they are spherically symmetric for a large class of phi. So some simple examples which you might come across in the literature are the so-called polytropic ansatz, where you simply prescribe a power law for the ansatz function. So how f depends on E, or the so-called King model, which is in some sense connected to a Maxwell-Boltzmann distribution, and physicists argue that this is a kind of natural ansatz function. Okay, so let me summarize. We have an ansatz function phi, and with that ansatz function, we actually get a whole family of steady states, which we parameterize by this central redshift. Right. And now we want to look at what stability behavior these family of steady states actually possess. So a few words on the numerics we're using. So of course we have to somehow simulate this on the computer, and we use a so-called particle in cell scheme or method for the dynamics of the system. This is quite common in this context. And the first step, of course, should be that you calculate the steady state. So calculate the steady state means you prescribe some ansatz function phi and some initial value for this quantity y. And then you solve this ordinary differential equation iteratively. This can be done with very high precision because we only have to do that once and only in the radial component. So this is possible very nicely. And then we have the steady state components, so the static metric basically, and the distribution function. Okay, so somehow we have to, and then what we call initialize the steady state. So we have to model this system in now three-dimensional phase space. And we do that by partitioning the phase space into little cells, and that putting in each cell a particle which has a specific weight which corresponds to the distribution function f. So then we have divided that phase space into cells and kind of initialized the particles in some sense. So this is actually quite a delicate step because there is no canonical way of how to divide the steady state into cells. So it might be very problematic to, for example, use cells which have a fixed volume, because then at the edge of the steady states, you might initialize way too many particles, and at the center where the galaxy may be very dense, you have too few particles. So you have to be very careful that this initialization actually reproduces the steady state, which you have calculated in the first step. Especially if the ansatz function is discontinuous in some sense, and this is very problematic, or this can be very problematic. All right, and then we have this distribution function modeled in phase space, and then if we want, we perturb the steady state slightly. For example, we can do that by modifying the weight of the particles by some factor which is close to 1. And a more physically intuitive setting would be that we nudge the particles inwards slightly or outwards slightly. So slightly really means very, very little because we want to check for stability. So we don't want to destroy the steady state totally. Okay, so we will come back to that nudging inwards and outwards a bit later. Okay, now we come to the step that takes the most time. That is the time step. So we assume that we have the particles' position and momentum at some time t. Then we can calculate this mass density rho and the pressure term p, which were given by integrals over v, so over the momentum variables, by simply, well, integrating or by summing over the particles through an interpolation, where the particles are smeared out over the radial coordinate by a head function. So this works quite well if you use a radial step, which is small enough. And then at that time t, we have the rho and the p term. And with that, we can go into the field equations, which tell us how the metric coefficients mu and lambda, how they look at time t. So we do that by a Runge-Kutta-4 algorithm, which is more than sufficient for our purposes here. And because in our case, we can explicitly solve for mu and lambda, so this is not too difficult numerically. So at this point, we have the particle positions, the momentum, the metric coefficients, and so on at time t. And now we do the actual time step and propagate the position, the momentum, and the weights of the particle according to the Vlasov equation. So according to the development equation for F and the characteristic system, which corresponds to that. So this, of course, has to be done for every particle. And if you work with a few million particles, this takes the most time on the computer. And yeah, this is the main step, which takes a lot of time numerically. So we use a bit more sophisticated algorithm to actually update this time step, but this should give a nice illustration of how we do it. So at this point, you can repeat the step again, because now you have the particle positions and momentum and weights at this increased time t plus delta t. And you can do this until you reach a prescribed time t, or for example, the stability which might emerge is apparent. So for example, you detect a trapped surface in these maximal areal coordinates. At that point, you can stop because you know this. You can call the steady state unstable because a black hole formed, for example. All right, so a few more details on the numerics. So we use about 10 to 100 million particles to really be sure that our system gets modeled correctly. This is actually really necessary, especially if we work in a highly relativistic setting. And how do we ensure that our system actually is close to the system, which is the full non-linear system from a mathematical point of view? So we look at the so-called ADM mass and the number of particles, which are just integrals over the whole phase space. And these quantities are conserved along real solutions of the Einstein-Vlasov system. And we check that they are also conserved here numerically, and it works quite well. Let's keep it like this. So even better if one, like one would imagine, I would probably say. Okay, so we are actually pretty sure that these dynamics which we capture numerically is really what happens in the nonlinear system. Okay, so one last quantity which we will use later on to look at the stability behavior is this quantity mu, so the symmetric coefficient evaluated at r equals 0. This is particularly nice because it consists of an integral over the whole phase space. So first of all, an integral over the radial component, and these components right here have already been integrated over the momentum variables. So this should be quite smooth in numerical sense. That shouldn't be prone to much errors. And also this quantity has some nice properties, or a physical interpretation at least, because if we look at e to the power of mu at this point r equals 0, this can be interpreted as the factor which with time moves slower at the center of the galaxy compared to the time at an infinitely removed observer who looks at the system from infinity. So e to the mu has a nice physical interpretation. So this is why we will only look at this quantity here in this talk. Okay, so let's look at some results which are known analytically and numerically. So first of all, there exists a kind of proof, or more or less a physical reasoning, let's call it that, from IPSA in the 1980s, which states that such a family of steady states, which we have obtained through this ansatz function, is stable at least, or linearly stable at least up to the first binding energy maximum. So we will see what the binding energy is, but this statement was put forward by IPSA in the 1980s. So nothing really happened from a mathematical point of view for quite some time until Hacic and Rhein took it among themselves to look at linear stability again, and they showed 2013 and 2014 that if you have stationary solutions which are not too relativistic, so this central redshift value is in some sense small, then you have linear stability in sense of a Antonov bound. So this was really one of the first, or maybe the first stability result in the system. And it makes sense also from a point of view if you reduce the relativistic setting in some sense, you arrive at the Vlasov-Poisson system. This was actually rigorously proven. And in the Vlasov-Poisson system, you know that such solutions are always stable, which they have looked at. So this makes sense that in some sense in the limit, in the Newtonian limit, these stationary solutions should be stable. So a quite recent result also with together with Lin, they have shown that if you do the opposite, so you increase the central redshift more and more, and with that increase the relativisticness, you get an exponentially growing mode for the linear system. So for large enough redshifts, you actually get a linear instability. This, this might also make sense because there should probably be a limit to when these stationary solutions are stable. Okay, so much for the analytical work. So much more does not exist, sadly. But numerically, there has been done quite some elaborate work, for example, by Harkon, and also by IPSA, Rhein, Shapiro, and Tucholsky, and so on. So there are quite a few people who have worked on this. And these numerical simulations always indicate that a so-called binding energy hypothesis, which was put forward by Seldovich and Podores in the 1960s actually, is valid. So they have also always found evidence for this hypothesis, which I will state here. So Seldovich and his colleague here suggested that a family of steady states, which you parameterize by this central redshift value, will be stable exactly up to the first maximum of the binding energy. And the binding energy is this quantity right here, which can in some sense be interpreted as the ratio of the rest mass of the system and the ADM mass, or the mass or energy of the system. So this hypothesis states that this family of steady states should become unstable exactly at the first maximum of the binding energy. And there's some physical reasoning, because Seldovich and Podores didn't have any numerical works or any analytical works we do not know of, but they reasoned physically, because often in physics, when you have a system which in some sense gets more unstable, for example, by increasing here this relativistic parameter in the sense of this redshift, the system counterbalances the instability which gets put into the system by increasing its binding energy. So this is kind of a general concept, if I have understood that correctly. And of course, this can only happen so far if we have not already reached the maximum of the binding energy. Because at that point, the system can't increase the binding energy further, and in some sense, instability sets in, and the system flies apart or collapses. So this was their reasoning for this hypothesis. And all the numerical results support this up until now. Okay, so I have talked about stability, like it is easy to see in such a numerical simulation. Of course, it might simply not be obvious what stability or instability means, but in our context, we can distinguish this actually quite nicely. So what might happen, for example, for a stationary solution which is stable? So here we have this polytropic case with k equals 1, so just a linear relationship of the energy and the density, and a central redshift which is not too large. Then it might happen that this galaxy, if perturbed slightly, starts pulsating or oscillating in some sense. So this is illustrated by this quantity e to the mu at r equals 0. So you can see that this oscillates quite nicely. Also, one should have a look at the time scales. Of course, this now you don't have a relation, but this will become clear in the next slides. This stability actually, or this oscillation actually, is quite nice for large number of time. So this is what might happen. Sometimes this oscillation is not as nice. Maybe there's some kind of damping effects, or numerical errors are too large, but this is one way to see stability. Okay, so what might also happen is, if the steady state is too relativistic, so here we have the same ansatz function, but a higher central redshift, is that the system might collapse to a black hole. So at that point, the matter rushes inwards to the center, kind of gets sucked in, you might call it, and at the center, eventually a trapped surface forms, at which point we stop the simulation because it gets more difficult to handle numerically. And this is represented by this quantity e to the power of mu here, and because we see that it decreases rapidly, at least after some initial time where it stays constant for quite a bit. And yeah, e to the power of mu actually, in some sense, approaches 0 if you continue the simulation here, but it gets much more difficult, which can be interpreted, as I told you earlier, that the time at the center of the galaxy actually moves slower and slower, and in some sense stops. So this maybe is what one might expect if the matter collapses. So this gets reproduced quite nicely. And also have a look at the time scale. This happens on much, much faster than these oscillations, which we have seen in the first slide. Okay, so this might happen in the case that we have nudged the particles inwards slightly. And now we look at the steady state, which the same steady state, which we have perturbed slightly differently, where we have nudged the particles outwards. So now the steady state does not collapse, but somehow it relaxes from this relativistic setting. This is represented by this initial increase in e to the mu. So the system gets much less relativistic, and but it doesn't fly apart completely. But at the center there remains matter. And if we have time, we can look at some animations which I have prepared. And it looks like there remains a new stationary solution at the center. So we have observed this phenomenon in a work which we have done at the University of Bayreuth 2 years ago. And this is also the reason why we have called it a heteroclinic orbit, because it looks like the system moves from a very unstable configuration to a stable new steady state at the center. And this looks like it stays stable, actually. Okay, so eventually, if you increase the central redshift even larger, it might happen that actually the steady state also disperses completely, so no matter remains at the center, and there is no kind of heteroclinic orbit here. But of course, this is difficult to see numerically, because you never know if you have waited for time long enough, or simply you have to wait longer, and eventually particles might come back at the center. But well, this is a technical discussion, I think. All right, so here's just an overview of these 3 situations, or 4. And you can see that the instability sets in quite quickly in time, and in contrast, the stable steady state just is basically constant in this quantity and also in different quantities. So this is not the only quantity we have looked at. Okay, so let's look at one example of an ansatz function which was used in very many numerical investigations. So this k = 1 polytropic ansatz. And first of all, we look at the binding energy curve, because this hypothesis states that we somehow can infer stability from this. So we have plotted the binding energy E, index B, on this vertical axis, and on the horizontal axis, we have the central redshift value. And we can see that the binding energy increases until it reaches a maximum at around the central redshift of 1/2. And then it starts decreasing. So if you put these steady states into our dynamical code, you can look for stability. And I hope you can see it. These blue dots, they were triangles. They correspond to stable configurations. And exactly at the, or at least numerically exactly at the point of the maximum of the binding energy, this stability changes. And after this binding energy maximum, the steady states become unstable. So this is indicated by the red dots. In this sense, unstable actually means that if you nudge the particles inwards, these steady states collapse to a black hole. So this happens rapidly at this point right here. So there's really a great quantitative or qualitative difference in these steady states at exactly that point. So this confirms this binding energy hypothesis. And this was, as I've already told you, observed in numerical work that was done earlier. So what are the new results from our work? So the main motivation was that these ansatz functions which were used for the steady states were always kind of similar. So this polytropic ansatz was used, this King model was used, And well, it was a little too similar always. This is why we have used, for our purposes, a new ansatz function, phi, which now depends on another parameter, I. And this is just a piecewise linear ansatz function. So this looks kind of difficult, but it's just a piecewise linear ansatz function where you have a very shallow increase in the ansatz function for small values of this parameter eta. And at some critical value, I over 1000, which then changes with I, of course, the ansatz function gets much more steep. And this we have.
I is 1, 2, 3, or is it 50,000, or what is it?
I'm sorry, I should have included that. That's a good point. I ranges from 0 to 1000. So if I is 200, for example, we have the change of this linear function at the point 0.2. Right. Okay, so and we have observed that this great increase in the steepness is actually very important for our results, which we have seen, which I will present now. So from an analytical point of view, there's no reason not to consider such ansatz function. Well, it is not differentiable at exactly one point, but this shouldn't be a problem, especially numerically, because one could always smooth that out. But from an analytical point of view, these ansatz functions phi assume fulfill every assumption which we need for so-called nice steady state. So it is there's no reason that the polytropic ansatz should be in some sense superior to this ansatz function right here, at least not to our knowledge. It is only much easier to use, of course. Okay, so first of all, you can look at binding energy curves for different values of I. So through this parameter I and the central redshift, we get basically a two-dimensional family of stationary solutions. And these are some qualitative behaviors of the binding energy curve, which might appear. So it might happen that, for example, for this red curve where I is equal to 50, the binding energy has a maximum very close to, or at very low values of the central redshift parameter. It might also appear that there are two maxima that are kind of close to each other. And a very peculiar value is also this I equals 300, where the binding energy basically stays constant, more or less, as soon as it has reached the maximum here up top. Okay, so this is already some nice, these are already some nice results, because such behavior was never seen for models which were used before. Okay, so let me now pick out a few values of I, which we will look at in more detail. So here I is equal to 200. So to recap, it's just an ansatz function which is piecewise linear in some sense. The exact value here doesn't matter for our purposes. And the binding energy curves looks qualitatively the same as in this polytropic ansatz. It increases and reaches a maximum and then decreases again for the central redshift set. But if we look at the stability behavior, these steady states remain stable for quite a while after this binding energy maximum. And at some point, they have to be unstable because of that result, at least in linear stability from Hatschich, Lin, and Rhein. And they change stability at some point, which we can't universally determine yet. But they do change stability and become unstable at around central redshift value of 0.8 in this case. So this is not a pathological situation. This actually works for a large number of values of I. So you could even call it that this is the normal situation that might happen. So this is already a new result. This was never observed, and it is strong evidence that this binding energy hypothesis, which was numerically confirmed up till now actually is not true. But note that the steady states are actually stable up to the first maximum, or at least to the maximum of the binding energy. Okay, so this next example where I is equals 270, the binding energy again looks very similar. Well, it has kind of two local maxima, which are followed quite closely after each other. And for small values of the central redshift, we see that these steady states are stable and very close to the maximum of this binding, or the first local maximum of the binding energy curve. They become unstable, so exactly like this hypothesis would expect. And there is an initial, there are values of the central redshift where instability sets in, but now something interesting happens. If you increase the central redshift further, you actually get a new area where the steady states are stable. So also this works for not only for this value I, but for a few. And of course, these steady states are very relativistic at that point. They are stable up almost to the central redshift of about 1, where our numerics really need high accuracy. This is probably the reason why such behavior was never observed before. But yeah, somehow these steady states are stable, and these configurations actually have a very dense core and some kind of halo around that. And somehow one might interpret it as the halo somehow stabilizing this very dense core, which is central at the center. Exactly. Okay, so this was also never seen before, and at some point, the steady states again become unstable, but we don't really know what is the cause of this instability, and we, to be honest, don't know what is the cause for instability right here as well. Yeah. So we have observed that behavior as well. Okay, so yeah, well, this is just an overview of all the models we have calculated in this I and ZC plane. Well, maybe you should just take away that we have checked our results with quite a few models. So our paper kind of raises more questions than it answers. Because before one would think that the stability behavior was kind of clear, but now it does not seem like there does exist some kind of turning point principle where one can infer from stability from that. And the question would be, if such a turning point principle exists, what would be the right quantity? We have looked at somehow modifying this binding energy or making it in some sense local, or have also looked at different quantities, but we have found no general rule of thumb or rigorous rule where stability changes. So this is quite interesting, especially compared with the fluid case of our systems, or the Einstein-Euler system, where stability, at least on a linear level, is where you can call it solved, because stability gets determined by the mass radius spiral, which was shown by Hadžič and Lin very recently. So in that case, a turning point principle exists, but well, this question might not be possible to answer, but it's still interesting why these systems behave so very differently. All right. So of course, still the question remains, why is the binding energy such a good criterion for a variety of steady states? So this King model and the polytropic ansatz, the binding energy maximum is exactly where the stability changes. So this could of course be coincidence, but maybe there's more behind that. And if we remember these steady states which were used by were looked at by IPSA in the 1980s, he has shown that linear stability, without using rigorous mathematics, he has shown that the steady states should be stable up to the first maximum of the binding energy, so at least, and we have always confirmed that. at least up to numerical accuracy. So this conjecture, you might call it, or formal proof still seems valid. And of course, a more formal proof would be or a more rigorous proof would be very interesting. And of course, one might ask the question if one can infer linear stability from a spectral analysis point of view. And we are currently working on that last point on a rigorous manner. But well, let's say it is not really that simple as one. Yeah, it is not simple. Let's keep it at that. Okay, so I don't know how much time I have already used up, but I have prepared a few animations. What stable and collapse and these heteroclinic orbits might actually be. So let us, I hope everybody can see it also at home. So let us look at a system which is stable. So what we can see here is the particle energy E and the radius R on the horizontal axis. And each dot basically represents one particle which we have simulated. And if one perturbs this steady state slightly, it stays stable. These particles fly around the center in orbits. So in the radial component, of course, you only see them moving forward and back. And the steady states kind of start pulsating. So here you can see it quite well that the lower where bound moves up and down in time slightly. So this is what happens for stable configurations. Okay. So now we look at a collapse, and we have again the same situation that we have this particle energy E and the radial component R, and steady state kind of first of all stays at the same place, but at some point the instability just sets in rapidly, and every particle in this case at least gets sucked in, and well, they get gathered here at a value which is close to the Schwarzschild radius actually of the whole system. So this might be the way collapse actually looks like. And maybe the nicest clip is this right here. So this is a heteroclinic orbit. And again, this system changes form quite rapidly and somehow relaxes. And this is depicted by basically this value of E increasing. And some packages of particles get flung out of the system. Eventually, they might be recaptured, but some leave indefinitely. And at the center, again, such a structure which looks like a stable steady state remains. And these particles which are captured back here, they fly around that steady state as well. And we don't know what this steady state actually is. So this is maybe another interesting question one might ask oneself. Okay, so much for these videos. And if you have any questions, please let me know.